Hello friends. So in this topic we will discussing on the what is mean by the multiple integrals. That is what is mean by single integral, what is mean by the double integral. Especially we are discussing here on the double integrals over a rectangle. So let's start with what is mean by the rectangle. So for the rectangle we have to define the partition of a rectangle. Actually rectangle is the region defined with some properties. So what is the rectangle? Usually a rectangle is denoted by capital R is equal to the points. As we are defining the multiple integrals, especially we are defining the double integral, so we are defining it is on R2. So x comma y belongs to R2 such that a is less than or equal to x, is less than or equal to b. Again y is less than or equal to greater than or equal to c, and y is less than or equal to d. So this is basically nothing but a lies between this closed interval, sorry, x lies between this closed interval a and b, and y lies between the closed interval c and d. So this is equal to the closed interval a comma b cross the closed interval c comma d, which is basically this, which is basically denote this, and it is called as a rectangle. It is called as a rectangle. It is called as a rectangle. Okay, now we are going to define partition of a rectangle, because in order to define the definition of a double integral we need these concepts. These are the very basic concept which may be asked in your MCQs. Okay, so their properties may be asked in the MCQs. So this is the definition of rectangle. So they may be vary this interval by open interval, maybe by semi open, semi closed. So they are asked which of the following represent a rectangle. So they may vary this closed interval by open. Okay, so you may keep in mind that in rectangle we have only the closed interval, the cross product of the closed interval, bounded closed intervals. Now the partition, we know that the partition, let P1 is equal to a is equal to x0 x1 x0 x1 x2 up to so on, xn is equal to b, be a partition of closed interval a comma b. Suppose P1 is the partition of closed interval ab, and P2 is equal to c is equal to y0 y1 y2 up to so on, yn is equal to d, be a partition of closed interval c comma d, be the partition of this interval, closed interval c comma d. Then define p is equal to p1 cross p2. Then define p is equal to p1 cross p2, which is equal to xi comma yi or xi comma yj, such that 1 is less than or equal to I comma j is less than or equal to n. Okay, so here maybe the points deeper what the points. So here is less than or equal to n, and j suppose lies between this, suppose this is t. So we have this set, it is called as the partition of the rectangular R. It is called as this partition of this rectangle R. It is called as the partition of the rectangle R. The partition P divide the rectangle R into sub rectangles. Okay, so the partition, actually the task or the work of the partition is that partition is that to divide the region or divide the set into equal parts. So this is the use of the partition. So the partition P divides the rectangle R into m into n sub rectangles, that is Rij is equal to xi minus 1 comma xi cross yj minus 1 yj. So this is the partition of this. So this is the sub rectangles. These are the sub rectangles, and which are the members of these our original rectangle a comma closed interval ab cross the closed interval cb. Okay, now this is about the rectangle, and we are defining the integral over the rectangle. So there is need to discuss these concepts, that is what is meant by the rectangle and what is meant by the partition. Then next definition is upper and lower Riemann sum. Next definition is that upper and lower Riemann sum. Upper and lower Riemann sum. So definition is that, what is the definition? Let F is a mapping from this rectangle AB cross CD to R. Let F is a real valued function, two-dimensional real valued function, be a bounded two-dimensional real valued function, be a two-dimensional real valued function, yes, be a real valued two-dimensional function. Next, let P is equal to P1 cross P2 be partition of this closed interval, of this rectangle AB cross CD. We just had discussed what is mean by the partition. Next, Rij is subpartition. What is Rij? Here we had discussed what is mean by the Rij. Rij is this, that is Rij is the subpartition. Rij is the subpartition. Next, let delta of Rij. What is the delta of Rij? Area of the rectangle Rj, which is equal to area of rectangular Rij, which is equal, what is the rectangular area of rectangular? Yes, length into height, which is equal to xi minus 1 into yj minus. Suppose this is our whole rectangle R, and suppose this is our Rij. This is suppose our Rij. This is our Rij. This is the whole rectangle AB cross CD. Suppose this is the whole rectangle AB cross CD, and this is, then the area is nothing but this length into height, length into breadth. So very basic formula. So this is what area of the subrectangle. Now define a function. Very important functions are these. Now let us define the functions. The function is, first one is LPF is equal to summation I runs from 1 to n, and summation j runs from 1 to t, mij delta rij, which is equal to summation I runs from 1 to n, summation j runs from 1 to t, mij. What is Rij? Rij is xi minus 1 into yj minus 1. Similarly, we can define UPF, which is nothing but the upper sum. Summation I runs from 1 to n, summation j runs from 1 to t, capital Mij into delta Rij, again, which is equal to summation I runs from 1 to n, summation j runs from 1 to t, capital Mij xi minus 1, yj minus yj minus 1, which is equal to yj minus yj. Now what are these Mij, small Mij and capital Mij? This small Mij is equal to what? Small Mij is equal to the infimum of this function x comma y over this x comma y belongs to this rectangle, subrectangle Rij. What is the function? It is originally defined the function which had defined defined from AB cross closed interval AB cross to closed interval CD, and this capital Mij is equal to supremum of this function f of x comma y, where again x comma y belongs to this subrectangular. These are the small Mij, this is small Mij, and this is about the capital Mij. Then this LPF, then the LPF is called LPF is called LPF is called lower Riemann sum, and UPF is called upper Riemann. LPF is called lower Riemann sum and UPF is called upper Riemann sum of this function f, of the function f. This is are the definition of lower Riemann sum and upper Riemann sum. So what is the lower Riemann sum? May I repeat? The lower Riemann sum is nothing but Riemann sum. How can we read this as? Lower Riemann sum of this function f with respect to partition P. Lower Riemann sum of this function f with respect to partition P is equal to summation Mij into delta Rij. We should know about what is mean by the delta Rij, where this I runs from 1 to n, j runs from 1 to t. Okay, and similarly upper Riemann sum of this function f with respect to partition P is equal to summation of capital Mij into delta Rij, where this I runs from 1 to n and j runs from 1 to t. This is upper bound, like upper bound, so it is infimum, so it is an supremum of this function f, over the rectangle Rij. Now consider the remark. Consider an useful remark. What is the remark? If f is equal to identity function, f is an identity function, then lower Riemann sum of this function identity is equal to upper Riemann sum of this function identity with respect to partition P is equal to the whole rectangle AB cross CD, where this I is defined from AB cross CD to R. If this I is defined from AB cross CD to R, then lower Riemann sum of this function I with respect to partition P is equal to upper Riemann sum of this function I with respect to partition P is equal to the rectangle AB cross CD. We will show you that how these two are equal. Summation I runs from 1 to n, summation j runs from 1 to t Rij. Okay, because here upper Riemann sum and lower Riemann sum are always yes. Okay. Instead of identity function, we had taken here the constant function 1. Constant function 1. If we take instead of this I, it is a constant function 1. Okay, sorry. Here is an correction. Instead of I, if we take the constant function 1, then which is equal to delta Rij, and summation I runs from 1 to n, summation j runs from 1 to n. This is what xi minus 1 and yj minus 1. Here the summation I, here is the variable I and here is the variable j, so we can separate it with respect to the sum xi minus 1. Summation j runs from 1 to t, here 1 to t, yj minus 1. If we solve this, we get this is a rectangle a cross b, and this is a rectangle, or we can say this is the length of length. This is nothing but, if we solve this, we get this is the length of b minus a, and this is the length of c, I think d minus c. If we solve these two, then we get this is the length of the interval AB and this is the length of the interval CD. So we get this is the area of the rectangle, area of this rectangle A cross B cross C comma D. Now an important theorem. Let R is a rectangular, let R is a rectangle and f is a bounded function defined on R, and f is a bounded function defined from this rectangle A comma B cross C comma D to R. Suppose this is a rectangle defined on R, and P be any partition of R, and P be any partition of R, P be any partition of R. Let this small m is equal to infimum of the function f of x comma y, where this x comma y belongs to this rectangle R, and capital M is what? Supremum of this f of x comma y over this rectangle R. Then we have the inequality. M into b minus a, which is less than or equal to m b minus a into d minus c, which is less than or equal to LPF lower sum, which is less than or equal to UPF, which is less than or equal to capital M into b minus a into d minus c. So we have a inequality. Which is very useful as for our exam point of view or for the next 2 or more theorems. So this is the inequality occurred by the mathematician Darbox. So it is also called as a Darbox inequality. So you see here, lower sum is always less than the upper sum, and upper sum is less than this. This is what? M into b minus a into d minus a, and the smallest term is this. So lower sum and upper sum are always bounded for a bounded function. Lower sum and upper sum are always bounded for the bounded functions. And if we see for the proof, first we have to choose a subrectangle. Then we are defining small mij and capital Mij on this Rij. Small Mij is the supremum of this function over Rij. Small Mij is the infimum of this function f on this subrectangle Rij. Capital Mij is also a supremum of this function f over this. Here we are defining small m and capital M. These are the infimum and supremum over R, over this. but this Rij is a subinterval, subrectangle, and we are defining Mij with respect to Rij, capital Mij with respect to Rij. Mij is supremum, small Mij is the infimum of this function f over this subrectangle Rij, and capital Mij is the supremum of this function f over this rectangle Rij. So we have the quantities. This Mij is infimum of xy over Rij. Capital Mij is supremum of f of x comma y over this Rij, over this rectangle Rij. So we can start with this small m into yj minus 1, which is less than Mij into yj minus 1, which is less than capital Mij yj minus 1, which is less than capital M into yj minus 1. Similarly, we can define it for xj also. And if we apply the summation to both sides of this inequality, then the summation does not get changed. The inequality does not get changed. And by applying the summation, we get that this m into d minus c is less than Mij. We can write here as summation j runs from 1 to t Mij yj minus 1, which is less than or equal to summation j runs from 1 to t Mij yj minus 1, and which is less than or equal to this capital M. Capital M is about capital M into d minus c. Capital M into d minus c. Similarly, we can apply here for xj also, and multiplying these two quantities. So if we apply this for xj also, we get m into small m into b minus a, which is less than summation I runs from 1 to n Mij xi minus 1, summation I runs from 1 to n Mij, here capital Mij, this is capital Mij, xi minus 1, which is less than capital M into b minus a. So suppose this is equation number 1, this is equation number. Multiplying equation 1 and 2 point wise, we get this small m into d minus c into b minus a, which is less than, if we multiply these two terms, then this is summation I runs from 1 to n, summation j runs from 1 to t, and we get a term Mij into Mij xi yj minus 1 into xi minus 1, which is the definition of lower sum. And if we multiply these two quantities, we get a upper sum. And if we take the product of these two, which is again less than or equal to, if we choose Mij, there is no change in this inequality because this is the inequality. If we take Mij instead of Mij square, then the inequality doesn't get changed. So we get this as LPF, which is less than UPF, which is less than capital M into b minus a into d minus c. So this is a Darbox inequality, and we will define the double integral with the help of this inequality. And now we are going to define a double integral. double integral over a bounded, always a bounded interval, bounded rectangle. Let F is a mapping defined from the rectangle A comma B cross C comma D to R. Let F is a two-dimensional real valued function. P is the partition. Always need to define a partition. Why there is a role of partition? If we suppose we are in R and if we are going to define integration, what is basically integration? Area under the curve. It is the basic definition of integration. So if we define a integration and if we find the area between these two curves, so how we will count this? We will count this with the help of a partition. By using the partition, we are dividing the x axis into number of subintervals. So this is the use of the partition, and we are drawing the rectangles. We are drawing here the rectangles. Now area of this whole region is equal to sum of the area of these rectangles, because we can calculate the area of the rectangle by using the simply the formula length into breadth, length into breadth. So here this is not a rectangle, but you can draw it by rectangle, and this is what the area which remain here, it is called as a error. It is called as a error, and we can easily calculate this area. Again here if we draw this, we draw this, we draw this, okay, we draw this, then we can calculate this, and which is the area. And if we draw the line below this curve, then this is called as a lower sum. And if we choose this, we can choose this rectangle also here, okay. And if we collecting the rectangles which are lies upper side of this curve, then this is called as upper integral, okay. So this is basically what is use of partition. In order to draw the rectangles, we are use the partitions. We are use the partitions. P is the partition, and just we had studied the inequality that LPF is always less than capital M into D minus C into B minus A, and UPF is always greater than or equal to small m into D minus C into B minus A. We have these inequalities. That is, LPF and UPF are the bounded terms, are the bounded functions. So we can define a set LPF such that P is partition of this closed interval AB, of this rectangle. So if LPF is bounded, then this collection of all the lower sum is also bounded by varying the partition. By varying the partition, every time we get the different. If someone choose this partition, someone choose a different partition also. So every time we get a different LPF and different UPF. Similarly, it is a bounded set and has a supremum or greatest lower bound has. Similarly, we have UPF where P is partition of this closed interval AB cross closed interval CD, of this closed interval AB cross closed interval CB. This is also bounded and bounded below, so has infimum or least upper bound, or greatest lower bound. It has upper bound which is least may exist, okay. So let's define L of F is equal to least upper bound of the set of this set. L of F is equal to least upper bound of this set, and G of F is equal to greatest lower bound of this set. And these are nothing but and if these two terms GF and LF are equals, or simply LF is called as a lower Riemann integral, LF is called as a lower Riemann integral, and GF is called as a upper Riemann integral, and if these two are equal, then the function is called as a double integrable, and it is defined with the help of integration over this rectangle AB cross CD f of x comma y dA. It is called as this. It is called as the double integral of the function f of x comma y over this rectangle a comma b cross c comma d by this function f, and it is obtained with the help of the partitions. Okay, with this we will stop here. Next in the next lecture we are discussing on the properties of the double integral. Okay, thank you.